Right. 1, 2, 3. I hope that works. All right. So as advertised, I will be giving the continuation of the talk that Emily started before the lunch break. So title is the same and the set of references is the same. So I'm not going to review them. Even though it's part 2, I should say that I thank the organizers for putting together a beautiful meeting and for inviting me to speak. So since it's after the lunch break, let me very briefly but firmly remind you of the conclusions of the first part. So here's a short summary. We start with n equals to 2 supersymmetric Yang-Mills theory with SUN gauge group. This is the n equals to vector multiplet. Phi are the complex scalars. Here are the 2 gauginos, which are doublets under the SU2R symmetry. Then the gauge fields, all of them are adjoints of the SUN gauge symmetry. And these 2 vial gauginos can be thought of as a single adjoint Dirac fermion. Now, the SU2R symmetry that acts on the gauginos is chiral, and only its U1 Cartan acts in a vector-like fashion on the Dirac fermion. Okay? So here is a brief flash of the Lagrangian in the UV. These are the usual kinetic terms for the gauge field, the scalar, and the gaugino. Here's the famous supersymmetric scalar potential that leads to flat directions to a moduli space of vacua. And here are the Yukawa couplings coupling the scalar to the gauginos. A small comment, because of the Yukawa couplings, the Vafa-Witten theorem does not apply in the supersymmetric theory. And in particular, it's not necessarily true that this U1 Cartan is unbroken. There's no argument to that effect. Now, as Emily reviewed for us in great detail, if you add this supersymmetry breaking non-holomorphic mass for the scalars, trace phi bar phi, then as long as the coefficient, the mass coefficient is big enough, as long as it's bigger than the strong coupling scale of the theory, then you can decouple the scalars and flow to pure adjoint QCD with 2 vial fermions and no scalars. This is a non-supersymmetric theory. And that theory doesn't have any Yukawa couplings because when you get rid of the scalars, you decouple them as well. And in particular, in adjoint QCD, the Vafa-Witten theorem holds, and you can prove that the vector-like Cartan, the U1R, inside SU2 must be unbroken. By the way, this Cartan is what in ordinary QCD you would call baryon number. All right. Yes. In principle, yes. You will see that we can do better, but in principle, yes. All right. Now, the second key ingredient to the story was that this non-holomorphic mass term is not just some garden variety operator, but it's actually an operator that sits in a multiplet that's protected by supersymmetry. In particular, this P is the bottom component of the n equals to 2 stress tensor multiplet, which means if you act with 2 Qs and 2 Q bars, you get the stress tensor. And we can track it explicitly to the infrared as long as the SUSY breaking is small enough. So that was the arc of the story in part 1. And the conclusion was that this operator, literally this trace phi bar phi mass operator in the UV, flows to the infrared scalar potential in the moduli space. And in particular, this implies, as I think Zohar asked in the first part, that there is a frame, there's a kind of duality frame on the moduli space where K is globally well defined. Okay, so this can be computed exactly from the Zyberg-Witten solution. And even though the details are complicated, it leads to a relatively simple picture because K is just this convex up function with a unique minimum at the origin where all of the U coordinates, or if you wish, all of the phi coordinates vanish. And there we get a SUSY breaking vacuum with massive scalars. So the scalars get a mass proportional to m squared, but nothing else gets a mass. You get n-1 photons and n-1 billion gauginos. No sign of chiral symmetry breaking or confinement in this small mass regime. So this was the end of the first part. This was the cliffhanger, if you wish. And the next question we should ask ourselves is what happens for larger value of the SUSY breaking? And this is the point where I need to be completely clear. If you are somebody who insists on absolute control and parametric control, you stop here. The end. Right? Because the EFT, the SUSY break, the supersymmetric EFT in the Coulomb branch is only valid at very low energies, and we can only track the SUSY breaking deformations for very small values of m. Right, so we lose strict effective field theory control if we try to dial up m. Very good. And there's also a pragmatic aspect to this, which is if you are faced with such a situation, what good would dialing up m even do? It would just make the scalars a little heavier, but it wouldn't fundamentally give you anything new. I think this is the question that you asked. All right. So I wouldn't give this talk if it weren't a good idea to push a little bit further. And the idea is that we shouldn't give up yet, because n equals 2 supersymmetry is not just good for controlling the massless modes and the action for the massless modes, it actually protects some of the massive degrees of freedom as well. So in the supersymmetric theory, you can actually compute the masses and charges of protected BPS particles. And this is another problem that's been studied to death in the context of n equals to 2 gauge theories. In particular, Lerche quite a while ago computed the BPS spectrum at the origin of moduli space using very indirect string theory arguments. And let's look at the BPS spectrum at the origin of moduli space. That's the point at which the small supersymmetry breaking lands us. So we decided what happens as far as the massless modes is concerned, but let's ask about the massive spectrum there. Well, you can compute the BPS masses. They're somewhat complicated. There's an exact formula in terms of hypergeometric function, but it turns out that the formula simplifies a lot if you look at the large n limit of SUN. And then you get a spectrum of BPS masses that looks like the strong coupling scale lambda multiplied by sine pi j over n, where j is an index that goes from 1 to n minus 1 and labels a tower of BPS states. Now, anyone who's played around with this class of theories will be interested by this sign factor appearing, and the sign factor will appear in various forms and guises throughout the talk. So what does this formula tell you? This formula tells you that the lightest BPS state has a mass of order lambda over n. So it's actually very light, especially at large n. And that's what sets your strict EFT cutoff. If you're a rigorous person, you're not allowed to dial up m beyond lambda over n, which is really a tiny number. And then on top of that, there's a spectrum of higher states. In the beginning, they're evenly spaced, and then they bunch up around m equals lambda. And there's a sort of dense spectrum up there if n is large enough. All right, so we know this exactly. This is an exact supersymmetric result. We know that these states are there. Moreover, at the origin of the Coulomb branch, you might remember that there's an unbroken Zn chiral symmetry that acts on the gauginos. And this is the remnant of the chiral U1R symmetry that remains after you take into account the Adler-Baljakov anomaly. And each of these states that I've indicated here is actually n-fold degenerate, because it transforms in the fundamental of this unbroken Zn symmetry. So every single level in this tower is n-fold degenerate. So this is in the middle of the strong coupling chamber. All the W bosons have decayed and become unstable, but there is some set of dions and monopoles that remain stable, and this is them. These are the only stable particles in the strong coupling chamber. No, I'm telling you that this is true. I'm not telling you it's automatic. I'm telling you that each level is n-fold degenerate and transforms in the fundamental of this Zn. Yeah, so it's not necessary, but it is true. And in total, there are n times n minus 1 states. Now, this picture, when you see it, well, the pessimist would say you should stop here. The optimist would say, if you keep going and you dial up your SUSY breaking, eventually you will hit these thresholds and you'll have access to these new degrees of freedom and to new directions in field space, and those might give you new and interesting vacua. So we're going to take the, I think, optimistic point of view and do that. Well, so these are the only states you have control over from supersymmetry. There's an expectation that at strong enough coupling, generically only the protected states should be stable, but there's no proof, of course. These are the fundamental objects. there are n times n minus 1 fundamental objects. It's not n, it's order n squared. Yeah.
Let's say
that's how it is.
for example.
No, in SU2, there are only 2. Yeah, but n times n minus 2 is 2 when n is 2. N times n minus 1 is 2 when n is 2.
So it's n.
Yeah. N minus 1 towers, and each tower is n-fold degenerate.
Everything else.
Correct. Those are the only stable ones. Yep. In a sense, this is by far the simplest chamber of the moduli space. In all other chambers, there are many more bound states that you can think of as bound states of these.
Yeah.
Yes. Okay, good. So this is the idea, but the challenge is to find a useful description of how to actually implement this, right? Because these are, first of all, they're massive states. Secondly, there are monopoles and dions at every level, and they're actually mutually non-local, because the Zn symmetry that rotates them into each other is intertwined with duality. And so the different members of the same Zn doublet, or the Zn multiplet, are mutually non-local. So you cannot write a standard useful description that involves all n of these states at every level. So you have some kind of problem. You need a useful quantum field theoretic description. And here I'm going to point out the following fact, which is going to hopefully help us along. Let's imagine looking at this tower of states at the origin and asking what these states do as you track to the multi-monopole point. Remember, Emily introduced the multi-monopole point as the point where n mutually local, n minus 1 mutually local monopoles become massless. What are these n minus 1 mutually local monopoles? You can actually see that there's exactly one state from each tower that becomes massless at this multi-monopole point. So each level in the tower is n-fold degenerate. And if you look at a single multi-monopole point, here I'm looking at it from the top, then one state from each level goes here, one state from each level goes here, and so forth. One state from each level goes here. And the states that become massless at a single multi-monopole point are all mutually local with each other. That's the beauty of the multi-monopole point. So there is a completely standard useful effective field theory that describes those n-1 states. And of course, you can't do all of them at once, but if you look at the totality of all the n monopole points, you will have actually described all the states in this tower. So the proposal is to use the effective description here in terms of the n-1 mutually local monopoles as an effective dual description of the whole tower. And we will see that the effective field theory there has data associated to it, its coupling constants mainly, that retain information about the massive states. So I'll have more to say about that. So that's the proposal. Now, once you buy this idea, then you can immediately focus on a single monopole point, because the n monopole points are just related by the Zn symmetry, which is spontaneously broken away from the origin. So physically, they're all equivalent, and we're just going to stick with one of them. We're going to do the analysis in around one of these points, and then conclude from that for what happens at all the other points. Well, the gap for some of the states, the gap is 0. The other gap states, I think, it's even worse. I think the lightest gap state there is lambda over n squared. Yeah, this has traditionally led people to say that the effective field theory is useless, especially at large n, and you shouldn't even try. And I'm going to convince you that you can get very sensible answers, including at large n. All right. So what is the dual description that I'm advocating? What I'm advocating is that you use the standard supersymmetric Lagrangian at the monopole point, the same Lagrangian that Zyberg and Witten studied, the n equals 2 abelian Higgs model that describes the U1s coupled to the monopoles. And on top of that, I'm going to deform that Lagrangian by putting in our SUSY breaking term. And again, because T is a protected operator, I can track exactly what T becomes in this abelian Higgs model description. And it'll be something a little bit more interesting than just the Kähler potential that we saw in the Coulomb branch. Let me first review the supersymmetric part of the Lagrangian. This is going to be an n equals 2 supersymmetric abelian Higgs model. There's going to be n-1 U1 gauge group factors here. I'm going to denote them as dual magnetic gauge groups because I'm focusing on the multi-monopole point. So I'm using a frame in which the monopoles are weakly coupled. These are the abelian vector multiplets. There are n-1 of them. Here's the vector multiplet scalar, a dual, the abelian gaugino, the gauge field. And then there are the hypermultiplets, the charged hypermultiplets. The hypermultiplet scalars are doublets of the SU2R symmetry. And then there are charged fermions that are neutral under the SU2R symmetry, right? And each hypermultiplet has charge 1 under one of these dual magnetic gauge groups, which means that each of these H's describes a single monopole of magnetic charge 1. All right. Very good. So this is the supersymmetric story. I should mention one more extremely important point about just the supersymmetric Lagrangian. This is a abelian gauge theory of rank n-1. So in principle, it has an n by n matrix of gauge couplings. And it's very important, as you will see, for our story that this n by n matrix of gauge couplings is not just a diagonal matrix. So this TMN is the matrix of gauge couplings for these U1s. And you see it has a diagonal piece that involves the log running, if you wish, coming from the monopole of charge 1 in every gauge group factor. That's diagonal, and that's the same for all the U1s. But then it has an interesting threshold piece, which I call here log of lambda mn. This is just some matrix. It's a threshold effect because it comes from integrating out the massive states. Okay, so it's not uniquely determined by the physics of the massless monopoles. And you can compute it from Seiberg-Witten theory. And this is another kind of fairly challenging computation that we had to do ourselves, or at least to do correctly ourselves. And this is the answer. In principle, yes. In principle, this retains knowledge of the massive BPS spectrum. But if you know a simple way of getting this formula from the massive spectrum, then I would like to know. Because, you know, in principle, there should be one, but it's not a trivial relationship by any means. Yeah. Anyway, so you get this matrix of threshold corrections, and you see it's not particularly complicated. It involves some elementary functions. Again, the signs of pi n over m make an appearance, so that might make you happy. And very importantly, it has these off-diagonal elements. And we will see that these off-diagonal elements are going to play a starring role in getting a lot of the physics that I want to talk about right. All right. So this is the matrix of gauge couplings. Now, even the supersymmetric model has a scalar potential. The scalar potential in my model is going to have two parts. It's the parts coming from SUSY and then the SUSY breaking part. Let me first remind you of the supersymmetric part. So first, there's a coupling between the vector multiplet scalars squared and the hypermultiplet scalars squared. Remember, the multi-monopole point is at the point at which all the A duals vanish, because the A duals are the vevs of the, well, if you wish, the masses of the monopoles are proportional to A dual. And that's what this coupling tells you, right? This coupling tells you that the monopoles, which are the H's, have masses proportional to A dual squared. Right? So, and then there's a standard supersymmetric D-term scalar potential, which, if you wish, comes from integrating out some auxiliary field, which I'm not showing you. And that's a quartic potential for the charged hypermultiplet fields. I'm writing it schematically here as h to the fourth, but it involves some complicated contractions of the indices on the edges, but a very particular set of contractions. And then the matrix in front is the inverse gauge coupling matrix, because it's the gauge couplings that determine the D-term scalar potential. So this is a very particular potential for the H's that comes just from supersymmetry. Yeah. Well, the running from the light states is taken account in the Wilsonian effective field theory by just retaining the light states. So I've schematically written it here with some choice of cutoff. Yeah, but that needs to be matched. Yeah, and the heavy states just give you the threshold. All right, so this is the supersymmetric potential. And in particular, this supersymmetric potential doesn't have any vacua where H has non-zero expectation value. You see, H appears only in a positive definite fashion, and only H equals 0 is possible. Now let's look at the supersymmetry breaking contribution to the potential. So there's going to be our SUSY breaking mass squared, big M squared. And then there's going to be this operator T, which I need to match to my abelian Higgs model. So I'm not going to describe in detail how to do that, but supersymmetry allows you to do it exactly. And this is the answer that you get. you get three interesting terms. The first term involves, again, an interesting constant, which is the sign, and then a tadpole for a dual, linear term in a dual. The second term is a positive mass term for a dual with the gauge coupling matrix in front. And the third term is a term we haven't seen before, because so far we've only looked at vector multiplet scalars. This is a hypermultiplet scalar, and you see that it enters this operator with a negative sign. Yeah, thank you. So this negative sign is crucial because it's a tachyonic mass for the monopoles, and it wants to make them condense. So let's explore the physics of this model at very small SUSY breaking. Remember that we already had a picture of what happens there, so we should better reproduce it. For very small m, the tadpole overwhelms all the other terms in the potential, and you can solve for the VEV. You'll find that the A duals, the vector multiplet scalar, get a VEV of this order, and this puts them somewhere near the origin of the Coulomb branch. And if you plug into this mass term for the H's, you conclude that the mass for the H's is roughly speaking this sign, which I told you was roughly speaking the mass of the BPS states at the origin. And you find that the hypermultiplet VEVs are 0. So this model at small m correctly captures the physics of the small m SUSY breaking phase that Emily described at the origin of the Coulomb branch, even though we're using a completely different description at the monopole point.
The monopole is very, very light.
No, the monopole mass comes exactly out the right order to describe the physics at the origin, because this tadpole is of order lambda for a dual. There's no condensate here. No, not yet. H hasn't condensed yet. Remember, in the small m phase, H didn't condense. Yeah, it's stabilized by this and by this for small enough m. Well, there's many tensions in these terms. This term wants H to condense, and you see that once H condenses, it's more plausible that A should be small because of this term. So there's a balance, and you need to analyze the scalar potential. We spent months and months doing that. So I'm giving you the very short version, and then I'm happy to go into a lot of detail. So these are not included in this effective description, except through the threshold correction. So I warned you that I was going to stretch myself beyond the limit of validity of these EFT rules, and I'm going to go as long as I can without running into a wall. Yeah. So the proposal, and these are the words. Here's the words. The words are that this is not just a effective field theory with a very low cutoff that you should stop trusting immediately. Instead, you should think of this as a dual description for the physics at not just very small m, but potentially larger m. And if we get encouraging results, then we gain confidence that the dual is actually good. If something bad happens, then it wouldn't surprise us because we're doing something illegal anyway. Yeah. All right. Yeah, I'm moving towards the end. So let me quickly summarize the two highlights that come out of analyzing this potential at larger values of m. As you dial up m further, you'll encounter a cascade of first order phase transition, because as m gets bigger, the tachyonic mass for the hypermultiplet starts kicking in, and they want to condense. And the way in which they condense is they condense in charge conjugation symmetric pairs. And these transitions do indeed roughly happen when the SUSY breaking scale hits the mass scale of the BPS particles at the origin, roughly this scale. And in particular, if you allow yourself to extrapolate all the way towards SUSY breaking of order lambda, then all the H's condense, all the U1s are Higgsed, and you get confinement with unbroken center symmetry. Very similar to the way that Zyberg and Witten and Douglas and Schenker got confinement in the supersymmetric theory, except there it happened already for parametrically small masses. Well, the gauge group will be smaller. There will be a few photons left, and a few H's will have condensed. So all the intermediate phases have some nice description. I'll say something about the chiral symmetry breaking in a second, but there will be some leftover photons in those phases. So only at the very end, when all the H's are Higgs, do you get a confined phase. So let me say something about chiral symmetry breaking. The H's are charged under the SU2R symmetry. These I's are doublet indices under SU2R. So when they get Higgs, when they condense, they also spontaneously break the chiral SU2R symmetry. Now that's good. We want chiral symmetry breaking in adjoint QCD, but there's a real problem here because there are many H's. And if they all condense in random patterns, you might get misalignment and the SU2R might be broken completely. But I told you that the Vafa-Witten theorem says that its cartan should not be broken. The SUSY theory is smart enough to tell us how this works. The way it works is that the alignment of the H's is completely fixed by the supersymmetric D-term potential for the H's. And in particular, this matrix or this inverse matrix of gauge couplings here. And if you only strip out the directional dependence of the H's in SU2R space, if you, in other words, trade the H's for some spin operator, some triplet in SU2R, what you find is that you get a ferromagnetic spin chain, which may be ferromagnetic or antiferromagnetic depending on the sign of this matrix T inverse. Now, T inverse is an object we computed from supersymmetry. And supersymmetry tells us that T inverse is negative. So this is a ferromagnetic spin chain, and all the VEVs align and give you an unbroken U1 cartan to the SU2. So you get the correct R symmetry breaking pattern from SU2R to the unbroken cartan. Now remember, at large M, the Vafa-Witten theorem was supposed to guarantee this, but we actually get it even at intermediate M's because of this physics. All right, I can say something about the gauge-Gino condensate, but maybe in the interest of time, I'll skip ahead. If somebody asks about that, I can say more. So in the all Higgs phase, in the large M phase, where every single Higgs has condensed, we have gotten rid of all the photons, and all the VEVs are aligned. And because of the off-diagonal couplings, there are no massless pseudo-Goldstone bosons. The only massless Goldstone bosons are the two Goldstone bosons that you actually are supposed to have from SU2R breaking to U1, and they describe a CP1 sigma model. And the CP1, it turns out, has the appropriate radius that it needs to have in this theory, which is a radius of order n rather than root n, because we're in a theory with adjoints. And this is the point at which we can make contact with what was expected and what Emily reviewed for the chiral symmetry breaking confining scenario for adjoint QCD. So we get a phase with full confinement and the correct pattern of chiral symmetry breaking. And this is not a rigorous prediction of small SUSY breaking, but it is a strongly well-motivated picture that emerges from this rather compelling dual description. Now, one small comment that I want to make at the end is that the dual allows you to compute lots of things that are not necessarily protected by SUSY. And one interesting thing that's not protected by SUSY are the confining strings of this model. The confining things, you can think of them as solitons wrapping CP1 in the sigma model description, but it turns out that that description has problems. If you uplift to the full dual description involving the U1 gauge fields and the Higgs fields and the fermions, you get a much better control description. So that's an interesting problem to study. I'm currently looking into that with a student. And actually, a related problem that you can also study using our Lagrangian is just the problem of strings in pure n equals to 1 SUSY Young-Mills, which are not BPS. Yeah. Yeah. And the fate of the zero mode more generally. Yeah. Okay.
They were not trying to also basically assume this what you got. How do you know there aren't other terms?
There are definitely other terms.
Then how do you know they don't?
Well, so some of them. So first of all, these are the leading terms that are dictated by supersymmetry, and also I've truncated to the renormalizable terms. One thing that supersymmetry allows you to compute is some non-renormalizable corrections to these terms, which are surely there. Yes. Absolutely. So this is the correct but pessimistic outlook, which is that at higher M, all of this will be corrected by lots of things, and the picture could indeed be different. And that's completely honestly correct. But then you have to believe in a lot of conspiracies. You have to believe that this truncated Lagrangian has all the right physics to describe confinement and chiral symmetry breaking in a highly non-obvious way, right? Requiring all the details of the numbers in this matrices and the coefficients that appear here. And then you have to believe that this whole picture is ruined by the higher corrections. That's possible. Yeah. Well, this is not a proof, but it's no. I think this is much better than NJM models. Yeah.
I just have a question. Maybe it's about the ongoing one. My question is how this model, this effective theory, this effective dual theory, what kind of anality determines what it gives? For example, suppose the gauge
Well, if I could answer your question, then.
For example, for SU2, suppose I have a loop that goes around twice rather than once. What would the string tension of that be compared to the string tension of a loop that goes around this one?
Okay, so I think maybe the first question that you're getting at is that, of course, in the full theory, the center symmetry is only Zn, so we only expect that these strings are stable modulo n. But the dual description that I'm working with does not include this breaking, because the breaking of the anality 2 string involves massive states, massive W bosons. Those are not included in this description. This description is abelian, and the strings are magnetic vortex strings, right? They're really superconducting strings in this description. And in this description, all strings are stable because there's an accidental enhancement of the Zn one-form symmetry to U1. That's right. So in principle, I could ask what is the charge 1 string tension, what is the charge 2 string tension, and so forth. I could calculate them all. And then I would have to remind myself that the charge 2 string is actually unstable, and maybe I'm less interested in that answer. But you could still hope, and of course, again, there's no guarantee like with any of this, but you could still hope that if you compute the tension of the charge 1 string, you would get something that is at least qualitatively kind of not completely off from the right answer. No, I think this is very misleading, because you could say the same thing about n equals 1 Suzy-Yang Mills. In the limit of small Suzy breaking, there's an accidental BPS-ness, but that gets broken. No, the full U1 model, I think, does not. I think that's not right. The CP1 model truncate, just the CP1 model on its own is a separate story. But this full abelian Higgs model, I think, will be much more interesting than that. Yeah. Yes.
So,
yeah.
You're seeking kind of decipher this kind of natural stability, right? I mean, so you're this point, because I remember, imagine that we would be not far from because it's place where the whole world disappeared, and it's a place where interaction is not right. And studying there.
The interaction is not small. The W boson disappears at very strong coupling. This doesn't.
Oh, there's a regional coupling, yes, but coupling is between this object which are experience there. I mean, this original coupling, the two, this change of the vector boson and this one is small there, and now we have this new object formed in some coupling, but I'm talking not about because you have long range, the function stability, and the sign of this form like interaction changes time in mechanical fluid.
Yeah.
So that before it was the attraction, and now it's the torsion.
Yes.
But the place near simple quantum mechanics. But my question was what you were saying that you are far away from it.
So the tadpole that I'm talking about actually always pushes you slightly inside the curve of marginal stability, slightly. So you're basically always in the strong coupling chamber, and you don't need to worry about these marginal effects.
which is a curve, it means that it means the interaction of fundamental object. It is the one which move like and this is nothing. And I think it should be worked with because this fundamental object describes.
I'm not describing the massive objects that jump at marginal stability. I'm only describing the ones that become massless at the monopole point. I'm very much not describing the physics of the massive states. If the massive states undergo some jumping. But
your fundamental object monopole.
I'm near the monopole point, and I'm describing the same. I can, but I'm not. All the physics I'm describing happens near the monopole point. Yeah.
Okay, so maybe there's
Is there another question?
Questions? We should move to lunch break, and I guess we have.
No. We already had lunch.
No, it's coffee break. Sorry, I had a light lunch. It's a coffee break, and we'll have a panel discussion. Thank you.